This chapter elaborates on object-oriented databases and object persistence. The object-oriented OO paradigm was first introduced by programming languages such as C++, Eiffel, and Smalltalk. Due to its expressive modeling power and formal semantics, the principles of OO have also been widely used in software development methodologies. However, for data storage and management, the adoption of OO proved to be less straightforward. In this chapter, we discuss various approaches for object persistence. First, we refresh the basic concepts of OO. This will be followed by a discussion of advanced OO concepts, such as method overloading, inheritance, method overriding, polymorphism, and dynamic binding. Next, we review the basic principles of object persistence. We then discuss OODBMSs, which is the core of this chapter. The chapter concludes with an evaluation of OODBMSs. Due to its popularity and ease of use, we use Java as the OO language for the examples. In object-oriented programming, an application consists of a series of objects that request services from each other. Each object is an instance of a class that contains a blueprint description of all the object's characteristics. Contrary to procedural programming, an object bundles both its variables, which determine its state, and its methods, which determine its behavior, in a coherent way. Let's consider an example of a class employee defined in Java as illustrated here. In this example, you can see a class employee with 4 variables: employee ID, name, gender, and dep, which represents the department where the employee works. Each variable comes with a getter and setter method, which allow to retrieve or modify the variable's value respectively. Other methods can also be added as needed. For example, a method to calculate an employee's salary. The getter and setter methods are also called accessor methods and implement the concept of information hiding, also called encapsulation. The main idea is to make variables private to the class, so they are not directly accessible from outside of the class. This gives the programmer control over how and when variables can be accessed. Encapsulation offers several advantages that make it standard recommended practice for all classes. For example, you can use the accessor methods to check for validity before changing a variable's value. If an invalid value is provided, the programmer can decide how to handle it by adjusting it or throwing an exception, for instance. The concept of encapsulation enforces a strict separation between interface and implementation. The interface consists of the signatures of the methods. The implementation is then based upon the object's variables and method definitions and is kept hidden from the outside world. Once the class has been defined, we can create objects from it. This code snippet illustrates how we can create 3 employee objects and set their names accordingly. We now elaborate on advanced concepts of OO. We discuss method overloading, inheritance, method overriding, polymorphism, and dynamic binding. Method overloading refers to using the same name for more than one method in the same class. The OO language environment can then determine which method you are calling, provided the number or type of parameters is different in each method. Consider the following example. Here, you have one method with the name read and no parameters, and a second method with the name read and one integer parameter. To Java, these are two completely different methods, so you won't have any duplication errors. As expected, in case the parameter I equals 1, then read1 will have the same effect as read. Method overloading is a handy feature when defining constructors for a class. A constructor is a method which returns an object of a class. By using method overloading, various constructors can be defined, each with their own specific set of input parameters. Consider a student class with two constructor methods as illustrated here. The first one takes both the name and birth date as its input argument, whereas the latter only takes the name and leaves the birth date unspecified. By defining these two constructors and using method overloading, student objects can be created both when the birth date is known or unknown. Inheritance represents an is-a relationship. For example, a student is a person, so the class student could be a subclass of the person class. An employee is a person too, so employee could be another subclass of person. An undergraduate is a student, and a graduate is a student, so you can create two additional subclasses of the class student. Staff and faculty might be subclasses of the class employee. A possible class hierarchy for this inheritance example is shown at the bottom of my slide. Each subclass inherits both the variables and methods from the superclass. A subclass can also introduce new variables and methods. Here you see the definitions of the person and employee class in Java. The person superclass has a name variable, a constructor method, and getter-setter methods. The employee class is a subclass of the person class. Note the use of the extends keyword, which specifies the inheritance relationship. The employee subclass also defines two additional variables: the idea variable and an employee object which represents the manager of the employee. It also includes a constructor method and the necessary getter and setter methods to enforce information hiding. Method overriding implies that the subclasses can override an inherited method with a new specialized implementation. Note that this is not related to method overloading discussed earlier. Consider the calculate GPA method from the student class. Assume the student class has a grades variable that contains all the students' grades stored in an array, for example. The calculate GPA method then just calculates the average of these grades as illustrated in the left code snippet. Now, suppose graduate students only get credit for grades above a certain minimum. For example, only grades of 80% and higher are accepted, and courses with a grade below 80 must be repeated. Then for the graduate class, you might want to calculate the GPA based only on those higher grades. To do this, you can overwrite the calculate GPA method and change the implementation by adding an if grade bigger than 80 statement as illustrated in the code snippet on the right. Polymorphism refers to the ability of objects to respond differently to the same method. It is a key concept in object-oriented programming and is closely related to inheritance. Because inheritance models an is-a relationship, one object can take on the variables and behavior of more than one class. According to the class hierarchy of the person example, a master is a graduate is a student, and a student is a person. So depending on the particular functionality desired, the OO environment might consider a particular master object as a master, a graduate, a student, or a person, because after all, a master is still a person. Every method needs to be bound or mapped to its implementation. There are two types of binding. Static binding binds a method to its implementation at compile time. In contrast to static binding, dynamic binding means that the binding of methods to the appropriate implementation is resolved at runtime, based on the object and its class. It is also called virtual method invocation, and is the binding used for methods to allow for polymorphism. When a method is overridden, there are multiple implementations that can be called, depending on the object in question. During execution, the OO environment will first check the class of the object that the reference object points to for the method implementation. If it doesn't exist, the system will look to the superclass. It will check the superclass above that if it still doesn't find a match, and so on throughout the entire class hierarchy. By searching from the bottom up, the most specific implementation, or the one from the class lowest in the hierarchy, will be the one used. Consider again the example of the GPA calculation, which calculates the average of grades for most student objects and the average of grades above a threshold for graduate students. Suppose you create a person program class to run your main method, as illustrated here. You have two student objects. John is a master, subclass of graduate, and Anne is an associate, subclass of undergraduate. To compare easily, assume they both have the same grades for 5 courses. When your main method reaches the print statements, it will first call the getName method for each object. For John, none of the master class, the graduate class, or the student class contain a getName method. Therefore, the master object inherits the getName method directly from the person class. Next, it will need to call the calculate GPA method for John. The master class does not contain a calculate GPA method, but the graduate class, the superclass of master, does. Dynamic binding looks at the type of object that John is, a master, and hence a graduate. Therefore, the calculate GPA method from the graduate class is called. For Anne, the same decision process occurs. There is no getName method in any of the subclasses, so the class hierarchy is considered to find that Anne is an associate which is an undergraduate, which is a student, which is a person, and the getName method from the person class is called. For her GPA, neither associate nor undergraduate has a calculate GPA method, so the student version of the method is called for Anne. The output will then be as follows: John Adams, 0.865, and Anne Phillips, 0.792. Since John is a master student, which is a subclass of graduate, only the marks above 0.8 will be averaged, or the result will be 0.82 plus 0.91 divided by 2 equals 0.865. Since Anne is an associate, which is a subclass of undergraduate, her average will be calculated as 0.72 plus 0.82 plus 0.91 plus 0.69 plus 0.79 divided by 5 equals 0.792. It shows two different GPAs, despite having the same grades, because dynamic method invocation allows different versions of the methods to be called depending on the object calling it. During OO program execution, a distinction can be made between transient and persistent objects. A transient object is only needed during program execution and can be discarded when the program terminates. It only resides in internal memory. As an example, think about graphical user interface or GUI objects. Persistent object is an object that should survive program execution. In other words, its state should be made persistent using external storage media. Think about employee objects or student objects which are created and are manipulated by the program. Various strategies can be used to ensure object persistence. In what follows, we discuss persistence by class, persistence by creation, persistence by marking, persistence by inheritance, and persistence by reachability. Persistence by class implies that all objects of a particular class will be made persistent. Although this method is simple, it is inflexible because it does not allow a class to have any transient objects. Persistence by creation is achieved by extending the syntax for creating objects to indicate at compile time that an object should be made persistent. Persistence by marking implies that all objects will be created as transient. An object can then be marked as persistent during program execution or at runtime. Persistence by inheritance indicates that the persistence capabilities are inherited from a predefined persistent class. Finally, persistence by reachability starts by declaring the root persistent object or objects. All objects that are referred to, either directly or indirectly, by the root object or root objects will then be made persistent as well. This strategy is adopted by the Object Database Management Group, ODMG standard, as we discussed later. Ideally, a persistence environment should support persistence orthogonality, which implies the following properties: persistence independence, type orthogonality, and transitive persistence. In persistence independence, the persistence of an object is independent of how a program manipulates it. In other words, the same code fragment or function can be used with both persistent and transient objects. Hence, the programmer does not need to explicitly control the movement of objects between main memory and secondary storage, as this is automatically taken care of by the system. Type orthogonality ensures that all objects can be made persistent, irrespective of their type or size. This prevents the programmer from having to write customized persistence routines and getting sidetracked. Finally, transitive persistence refers to persistence by reachability, as we discussed before. An environment supporting persistence orthogonality allows for improved programmer productivity and maintenance. Persistent programming languages were a first attempt to equip programming languages with the ability to preserve data across multiple executions of a program. This usually boiled down to extending an OO language with a set of class libraries for object persistence. One approach to do so is by using a mechanism called serialization, which translates an object state into a format that can be stored, for example, in a file, and reconstructed later. In Java, serialization can be accomplished as illustrated here. This program creates 3 employee objects, Bart, Seppe, and Wilfried, and sets the name variable accordingly. We now wish to make all 3 objects persistent. The object outputStream class will serialize an object to a file, myfile.ser, using the writeObject method. The objects will be stored as a sequence of bytes, including the object's variables and their types. In this case, Java will apply persistence by reachability. This implies that if the employee objects would have references to address objects, department objects, etc., then these will also be made persistent in myfile.ser. Once stored, the object can be deserialized from the file and recreated in internal memory using the class Object InputStream. Serialization is one of the simplest strategies to achieve persistence. However, this approach suffers from the same disadvantages of the file-based approach to data management. Another significant problem relates to the object identity that is lost. Suppose we store information about lecturer and course objects. Bart and Wilfried both teach database management, whereas Seppe and Bart both teach basic programming. This can be visualized in the object graph you see here. Assume we now serialize both the database management and basic programming course objects. This means the information of the Bart lecturer object will be duplicated. Upon deserialization, the Bart lecturer object will also be duplicated in internal memory, which can lead to inconsistencies when its values are changed during program execution. Hence, a better alternative would be to work with an object-oriented DBMS, as will be explained in what follows. Object-oriented DBMSs, or OODBMSs, store persistent objects in a transparent way. They originated as extensions to object-oriented programming languages such as C++ and Smalltalk, which included class libraries to make objects persistent. These libraries were then gradually extended with database facilities such as querying, concurrency control, and transaction management. Since these libraries and extensions were programming language dependent, no universal standard, similar to SQL in relational databases, was available to explain the heterogeneous OODBMS landscape. OODBMSs support persistence orthogonality, whereby the same data model is used for transient and persistent objects without any need to map to an underlying relational structure. As mentioned, they come with all the facilities of a traditional DBMS, such as a data definition and data manipulation language, query facilities, transaction management, concurrency control, backup and recovery facilities, etc. OODBMSs guarantee the asset properties discussed earlier for all persistent objects. In an OODBMS, every object has a unique and immutable object identifier, OED, which it keeps during its entire lifetime. These OIDs are used to uniquely identify an object. No two objects can have the same identifier, and each object has only one identifier. An OID is different from a primary key in a relational database setting. A primary key is dependent upon the state of a tuple, whereas an OID is not dependent on an object state. Consequently, a primary key can be updated, whereas an OID never changes. A primary key has a unique value for each tuple within a relation, while an OID is unique within the entire OO environment. In most commercial implementations, the OIDs will remain invisible to the user. They are typically system-generated. The OIDs are used to identify objects and to create and manage references between objects. The references can implement relationship types. By using these OIDs, it becomes possible that an object is shared by various other objects by simply referring to its OID. This reduces the amount of updates when objects have their variable values or state changed. Because of the extensive use of these OIDs, the object-oriented model is often referred to as an identity-based model. The relational model, on the other hand, is a value-based model, since it uses primary and foreign keys which are based on actual data values. A difference can be made between object equality and object identity. Two objects are said to be equal when the values of their variables are the same. However, this does not automatically imply that their OIDs are the same. A further distinction can be made between shallow and deep equality. To illustrate both concepts, assume we have a purchase order object with some variables, including a list of references to OIDs of related purchase order line objects. Shallow equality implies that two purchase order objects have the same values for their variables, such as purchase order number, purchase order date, supplier number, etc. Deep equality implies that two purchase order objects have the same values for their variables, and all their referred purchase order line objects have the same values for their variables as well. Two objects are said to be identical or equivalent when their OIDs are the same. In other words, even though the values of an object's variables may change, its identity always remains. The Object Database Management Group, ODMG, was formed in 1991 by a group of OO database vendors to define standards for working with OODBMSs. Its name was changed to Object Management Group, OMG, in 1998 to expand its coverage to both OODBMSs as well as Object Relational Mapping standards, which we discussed later. The primary goal was to promote portability and interoperability for object persistence by introducing a data definition and data manipulation language similar to SQL. The application developer should be able to use only one language for dealing with both transient and persistent objects. The OMG group introduced 5 standards. the most recent being ODMG 3.0 in 2000, which consists of the following key components: the object model, which provides a standard object model for object-oriented databases; object definition language, ODL, which specifies object definitions, classes and interfaces; object query language, OQL, which allows to define select queries; language bindings, for example for C++, Smalltalk, and Java, which retrieve and manipulate object data. Although the group disbanded in 2001, many of the concepts and ideas put forward have been implemented in modern OODBMSs and Object Relational Mapping frameworks. The object model serves as the backbone of the ODMG standard. It provides a common model to define classes, variables or attributes, behavior, and object persistence. Its two basic building blocks are objects and literals. Contrary to an object, a literal does not have an OID and cannot exist on its own. It represents a constant value and is typically embedded in an object. Three types of literals are supported: atomic, collection, and structured literals. Examples of atomic literals are short, short integer; long, long integer; double, real number; float, real number; boolean, true or false; char, and string. A collection literal can be used to model a collection of items. ODMG defines the following collection literals: set, which is an unordered collection of elements without duplicates; bag, which is an unordered collection of elements which may contain duplicates; list, which is an ordered collection of elements; array, which is an ordered collection of elements which is indexed; dictionary, which is an unordered sequence of key value pairs without duplicates. A structured literal consists of a fixed number of named elements. ODMG has predefined the following structured literals: date, interval, time, and timestamp. User-defined structures are also supported, such as address, as you can see illustrated here. The Object Definition Language, ODL, is a data definition language, DDL, to define the object types that conform to the ODMG object model. It is independent of any programming language. Similar to an SQL scheme being portable across RDBMSs, an ODL scheme can be implemented using multiple ODMG-compliant OODBMSs. Here you can see an example ODL definition for the employee administration we discussed before. The example starts with defining the employee class. A class is defined using the keyword class. The extent of a class is the set of all current objects of the class. A variable is declared using the keyword attribute. An attribute's value can either be a literal or an OID. Operations or methods can be defined by their name followed by parentheses. The keywords in, out, and in-out are used to define the input, output, and input-output parameters of the method. The return types are also indicated, whereby void indicates that the method does not return anything. To support the concept of encapsulation, it is recommended to add getter and setter methods for each of the attributes. The implementation of the operations is provided through the language bindings. Relationships can be defined using the keyword relationship, which we discuss in more detail in what follows. Here you can see the manager and department classes. The extends keyword indicates the generalization relationship between manager and employee. Remember that a subclass inherits the attributes, relationships, and operations from the superclass. Note that in ODMG, a class can have at most one superclass, so no multiple inheritance of classes is supported. Here you can see the project class definition. Here you can see the main ideas summarized once more. Since we already introduced them when discussing the example, we will not repeat them. Relationships can be defined using the keyword relationship. Only unary and binary relationships with cardinalities of 1 to 1, 1 to n, or n to m are supported in ODMG. Ternary or higher relationships and relationship attributes need to be decomposed by introducing extra classes and relationships. Every relationship is defined in a bidirectional way, using the keyword inverse, through which both directions have names assigned to facilitate navigation. For example, consider the 1 to n relationship between employee and department illustrated here. The name works in will be used to navigate from employee to department, whereas the name workers is the inverse relationship used to navigate from department to employee. Since a department can have multiple employees, we use the set to model the collection of employees working in a department. Other collection types, such as a bag or list, can also be used to implement the relation. For example, a list could be useful if we want to order the employees based on their age. An n-to-m relationship can be implemented by defining collection types, set, bag, etc., in both classes participating in the relationship. Consider this n-to-m relationship between employee and project illustrated here. This contrasts with the relational model where a new relation must be introduced. Based upon the relationships defined, the OODBMS will take care of the referential integrity by ensuring that both sides of the relationship remain consistent. For example, when adding a project to the set has projects of an employee, the OODBMS will also add the employee to the set has employees of the corresponding project. Object Query Language, OQL, is a declarative, non-procedural query language. It is based upon the SQL select syntax combined with OO facilities, such as dealing with object identity, complex objects, path expressions, operation invocation, polymorphism, and dynamic binding. It can be used for both navigational or procedural, as well as associative or declarative access. A navigational query explicitly navigates from one object to another. Here, the application program is responsible for explicitly specifying the navigation paths. This makes it quite similar to procedural database languages that came with hierarchical and codacil DBMSs we discussed previously. A navigational OQL query can start from a named object. Assume we have an employee object named Bart. The OQL query bart.dateofbirth returns the date of birth of Bart as a literal. In case we are interested in the address, we can write bart.address, which returns the address of employee object Bart as a structure. If we are only interested in the city, the query can be refined to bart.address.city. Note how we use the dot operator for navigation. An associative query returns a collection, a set or a bag, of objects which are located by the OODBMS. We can also start from the extent, which represents the set of all persistent objects of a class. The most straightforward associative OQL query then simply retrieves all objects of an extent as illustrated here, employees. If we want more specific information, we can write an OQL query with the following syntax: select from where. As with SQL, the select clause indicates the information we are interested in. The from clause refers to the extent or extents where the information should be retrieved from. The where clause can be used to define specific conditions. By default, an OQL query returns a bag. If the keyword distinct is used, a set is returned. Queries with order by return a list. Associative OQL queries can also include navigation paths. Consider the example illustrated here. Select e.social security number, e.ename, e.address, e.gender from employees E, where e.name equals Bart Bassens. This query returns the social security number, name, address, and gender of all objects of the extent employees where the name is equal to Bart Bassens. Note that the extent employees has been bound to a variable E as a shortcut notation. Suppose now that the employee class has a method age, which calculates the age of an employee based upon the birth date. We can then extend our previous query as follows. Select e.social security number, e.ename, e.address, e.gender, e.age from employees E, where ename equals Bart Bassens. Besides literal values, an OQL query can also return objects as follows. Select E from employees E, where E.age is bigger than 40. This query will return a bag of employee objects whose age is above 40. Just as in SQL, multiple classes can be joined. This can be accomplished by traversing the paths as defined in the ODL scheme. The first query, illustrated here, retrieves all information of employees working in the ICT department. The variable D gets bound to the department object based upon the following path, e.worksin. Contrary to SQL, you can see no join condition. Instead, the traversal path e.worksin ensures the correct department information is used. Multiple traversal paths can be used in an OQL query. Consider the second query. Select e1.ename, e1.age, d.dname, e2.ename, e2.age from employees E1, e1.worksin D, d.managed by E2, where e1.age is bigger than e2.age. This query selects the name and age of all employees who have a younger manager, the name of the department they work in, and the name and age of their manager. Like SQL, OQL provides support for subqueries, grouped by having an aggregate operator such as count, sum, average, max, and min. For example, the number of employees can be determined using the following simple query: count employees. The exists operator can also be used. The second query retrieves information about employees who have been working on at least one project. Suppose both the employee and manager class each have their own operation salary. Consider the following OQL query. Select e.social security number, e.ename, e.salary from employees E. This query will calculate the salary for all employee objects. Thanks to polymorphism and dynamic binding, the correct implementation of the salary method will be invoked at runtime for both manager and regular employee objects. A key difference between relational and OO database management systems is that the latter cannot be used without a particular programming language. ODMG language bindings provide implementations for the ODL and OQL specifications in popular OO programming languages such as C++, Smalltalk, or Java. The Object Manipulation (OML), the Object Manipulation Language (OML), is kept language-specific in order to accomplish a full and transparent handling of both transient objects in internal memory as well as persistent objects in the database. As mentioned before, the goal is that the programmer can use only one language transparently for both application development and database manipulation. For the Java language binding, for instance, this goal entails that Java's type system will also be used by the OODBMS, that the Java language syntax is respected, and that the OODBMS should handle management aspects based on Java's object semantics. For instance, the OODBMS should be responsible for persisting objects when they are referenced by other persistent objects. OODBMSs offer several advantages. First, they store complex objects and relationships in a transparent way. By using the same data model as the programming language to develop database applications, the impedance mismatch problem is no longer an issue. The success of OODBMSs has been limited to niche applications characterized by complex, nested data structures where an identity-based instead of a value-based method of working was better performing since it avoids expansive joins. An example is the processing of scientific datasets by CERN in Switzerland, where data access follows predictable patterns. The widespread use and performance of RDBMSs, however, proved hard to displace. The ad hoc query formulation and optimization procedures of OODBMSs are often inferior to relational databases, which all adopt SQL as their primary database language combined with a powerful query optimizer. Furthermore, when compared to RDBMSs, OODBMSs are not that developed in terms of robustness, security, scalability, and fault tolerance. They also don't provide a transparent implementation of the three-layer database architecture. More specifically, most OODBMSs do not provide any support for defining external database models, such as views in the relational model. Most mainstream database applications will typically be built using an OO programming language in combination with an RDBMS. In such an environment, an Object Relational Mapping (ORM) framework is used as middleware to facilitate the communication between both environments, the OO host language and the RDBMS. In this chapter, we started by reviewing the basic concepts of object orientation. This was followed by a discussion of advanced OO concepts, such as method overloading, inheritance, method overriding, polymorphism, and dynamic binding, all illustrated in Java. We then introduced the basic principles of object persistence and reviewed serialization as a first attempt to equip programming languages with the ability to preserve data across multiple executions of a program. This quickly brought us to OODBMSs, where we started by introducing object identifiers, which play a key role in identifying objects. The ODMG standard was covered next, and we discussed its object model, the object definition language, ODL, the object query language, OQL, and its implementation through language bindings. The chapter concluded by a critical review of OODBMSs. The chapter is based upon our book, Principles of Database Management. In case you want more information, I'm happy to refer you to the website at the bottom.